Hello, welcome again to the lecture series on control systems engineering. In this session, we'll carry out stability analysis. So under this, in this session, we'll differentiate differential equation and characteristic equation. We'll explain different types of roots of characteristic equation and find the roots of higher order characteristic equations, represent the roots in S-plane and able to represent the root behavior on time plane, means the system behavior on time plane, then create zones of stability and unstable on a mathematical plane. We'll define stable system, unstable system, relatively stable, absolutely stable, and critically stable system, and establish the necessary condition for stability. And we'll use Routh stability criterion to find the stability of systems. So as I mentioned in the beginning, there are three important things. One is finding out the system response, that is relative stability, that we discussed in the previous chapter. Now another important thing is we should know system is stable or not, and also we should learn how to design the system for achieving the required stability. See, we know, first let me explain what we mean by characteristic equation. Suppose I have a differential equation, that is m, say d square y by dt square plus c dy by dt plus ky say is equal to say kx. So then this is the differential equation of say spring mass damper system. Then when I take Laplace, this is y of s by x of s, then I get, by organizing all these things, omega n squared divided by s square plus 2 zeta omega ns plus omega n square. Correct? Let us say, when I write the control system equation, control system, if I represent by a block diagram like this, I'll get g of s, then h of s, like this. This is, this is r of s, this is c of s. Okay, then we got c of s by r of s is equal to g of s divided by 1 plus g of s h of s. Plus g of s h of s. Right. This 1 plus g of s h of s, I equate it to 0. And I call this as characteristic equation. Okay. Now, suppose here s square plus 2 zeta omega ns plus omega n square is equal to 0 is the characteristic equation. This equation, it is in the form of a square plus bx plus c. Correct? So then I will get two roots, s1 comma s2, and the roots can be, if I solve this equation, depending on the value of zeta, roots can be 1. Both the roots can be simply imaginary roots. Imaginary roots. 2. You may get complex conjugate roots. Complex conjugate roots. And 3. Unequal real roots. Unequal real roots. Okay. If the roots are imaginary, they lie here. The roots are complex conjugate, you know that, they lie here. And if the roots are equal and real, they lie on the negative real axis of the S plane. So please remember, this is all S plane, this is sigma and this is j omega. So this we have understood in the previous chapter very well. Now, if you see, like if you study the response of the system based on the location of the roots, suppose both the roots are, let us say, imaginary roots. Like this. So you are getting imaginary roots. That means actually zeta value is equal to 0. If I plot the response of the system, it will be continuously oscillating with constant amplitude. If you have complex conjugate roots, you can always find out theta. This is zeta is equal to 0 line and zeta is equal to 1 line, and this is an underdamped system, and the response will be oscillating. It will be oscillating, gradually it will damp down and settle down like this. Right? Suppose if you have, right, real roots, so that also I have explained, gradually it will decay down. So here I have shown a single root. Suppose two equal real roots you get, then gradually it will decay down and finally it will settle down. Suppose if I put zeta is equal to 1, then you are going to get two equal real roots you get. So that gradually it will decay down and finally it will touch this line. So in all these cases, you can observe that the roots are on the left hand side of S plane. This is S plane. Here the roots are located on the left hand side, here in these two. So gradually the output will settle down. Here the roots are on the imaginary axis. Continuously it will be oscillating. If you see here, if you have a root on the right hand side of S plane, then if I solve the equation and draw the response, right, it will be continuously as the time increases. This will also be increasing. For example, in this case, a solution can be of the form e to the power of minus t. Here the solution can be of the form y is equal to e to the power of e to the power of plus t. So here as the t increases, y value decreases, and when t becomes infinity, this will meet this line. Here when t is equal to 0, e to the power of 0, 1, as t increases, gradually the value of y increases. Same way, if you have two complex conjugate roots, the solution becomes oscillatory and the amplitude of oscillation gradually increases. Suppose you have a root at the origin, then you have something constant output like this. So looking at these graphs, what is important over here? Where the roots are located, what is the response of the system? This we have to observe. In this case as well as in this case, right? In this case as well as this case, roots are lying on left hand side of S plane. Correct? And the response is gradually dying down. Correct? So transient response, particularly time response, will die down like this. If the root is on the imaginary axis, you can see the response is oscillatory. If the root is on the right hand side, correct, here as well as here, you can say the response is building up with respect to time. Here if there is a single root at the origin, again the response is constant. So based on this, we can define stability of the system. You can say this system as well as this system, a stable system, you can say. These two systems, you can say unstable system. Unstable system. Here it is oscillatory, depending on the amplitude we can decide. Okay, so whether it is limitedly stable or marginally stable, whatever it is. Same case here also, right? Thus these root location help us to define different types of stabilities, like stable, unstable, limitedly stable. All these things we can define now. Please clearly understand, once you have a system, if you know its characteristic equation, from the characteristic equation if you can get the roots and see the location of the roots, also corresponding response. The response should be seen on time plane and location of the roots should be seen on S plane. If the roots are located on the left hand side of the S plane, you see the transient response will die down. Then such systems will become stable systems. If the roots are on right hand side, the transient response is building up, then such system will become unstable. Depending on the amplitude here, we can consider it as marginally stable or limitedly stable system. Now let us define like this. So whenever the roots are in this region, it is a stable region. Stable region. Here it is unstable. If the roots located, whether the roots are on the positive real axis or roots are again complex conjugate but lying on the right hand side of the S plane, make the system unstable. So while designing, you want to design a stable system, it is necessary that the root should be located on left hand side of S plane. So now let us define. So I have taken a control system, and I have shown a reference input and I have also shown a disturbance input. So the total output of the system is output due to reference signal, output due to disturbance signal. Here CD of t is equal to C of t minus CR of t I have written. When t becomes infinity, t tends to infinity, what is the response due to disturbance is my question. So let us understand what exactly the disturbance means. So assume you have a road like this. Okay. And you assume that you are driving your car in this lane. You are driving this car at a speed of something like, say, 120 kilometers per hour. This is the set speed. You are going in that speed. Assume all of a sudden another car enters in your path. So it will be a surprise for you. Because of that, what you do to avoid this disturbance, probably try to steer your vehicle like this. So when you steer your vehicle, simply the vehicle may oversteer and go like this, or your system may follow this path. So then this condition, what you can call it as oversteering, we call it as an unstable condition. You have done it, it is stable, fine. So this is what we mean by a disturbance. When a disturbance enters into your system, what happens? If the output due to such a disturbance die down with respect to time, then you can call that system as stable system, like what has happened here. If the response due to disturbance becomes plus or minus infinity, then we say unstable. This is the case, unstable. It remains some constant value, then you can say limitedly or marginally stable. In other words, we say you are given a bounded input. So you have seen in the previous case, let us say a bounded input like this. Your system output is also bounded. Means if this is the input, your system oscillates like this and finally settles down. This is a stable case. You are given a bounded input. Your system output is also bounded. If you take this case, you are given a bounded input. So your system response builds up like this. It becomes unbounded, unstable. Or it remains a constant, then I call it as limitedly or marginally stable. Okay. If you have to still understand, like the same car, when you are driving with, let us say, with a high speed, due to some disturbance, you brake the system. Okay, your vehicle may slow down and finally stop. That's one possibility. Okay, another possibility is that your vehicle may spin around. This is an unstable case. This is first one is a stable case. So that's how we can define those things. So even car like this can be modeled, and we can study when we brake what really happens like this by studying its response. So now the definition is like this. Stable. A system is stable if every bounded input produces a bounded output. Alternatively, a system is stable if its impulse response approaches zero as time approaches infinity. You have seen that. Response should approach 0 as time reaches infinity. The response is most of the time of the form, let us say e to the power of minus t. As t becomes infinity, it will die down. Unstable means a system is unstable if its response to a bounded disturbing force ultimately becomes an infinite amplitude or an oscillation of infinite amplitude or both. So, as I said, the response may simply build up like this, or the response may simply start oscillating like this, and with respect to time the amplitude builds up like this. That is the one. Limitedly or marginally stable. The response to a bounded disturbance ultimately becomes a constant or a constant amplitude oscillation or both, depending on the amplitude of the ultimate disturbed response. Such a system may be treated as stable or unstable. As I said, it may start oscillating with constant amplitude. It will not stop, but the amplitude. So depending on the amplitude, you can say it's marginally stable system or unstable system. You can decide depending on your requirement. Correct. Or the output, simply between the output and input, there will be a constant value. This we call it as limitedly or marginally stable. So stable, unstable, limitedly or marginally stable. So system to be stable, as I mentioned, all the roots must lie on the left hand side of S plane. If the roots lie on the right hand side of S plane, the system will become unstable. If there is a root at the origin, or if there are imaginary roots like this, then you may find limitedly or marginally stable system. Okay, right. Absolutely stable. A system is absolutely stable with respect to a parameter of the system if it is stable for all values of this parameter. Whatever you do, right? So you disturb, the system is here, you disturb it, it will go back, go here, but it will come back to the same point, right? It is absolutely stable. Conditionally stable. A system is conditionally stable with respect to a parameter of the system. It is stable for only certain bounded ranges of values of this parameter. Correct? Suppose for particular values of zeta, it may remains a particular value of gain k, it may remain stable. Okay, for lower values of gain k also system may become unstable. Higher values of gain k may also becomes unstable. So such a system we call it as conditionally stable. Otherwise this is absolutely stable. Okay, it is the quantity to see, later I will discuss about this in the root locus plot. So there are systems. Okay, the value of the gain always, suppose if the transfer function of the system is open loop transfer function of the system is something k divided by s into s plus 2, s plus 3, like this we have. For whatever be the value of the k, the roots always lie on the left hand side. Then it is absolutely stable. Some systems are not like that. When I draw the roots positions like this, here the k value, different values of k, here it is on the right hand side unstable, but if I increase the k value beyond a certain point, roots come to the left hand side. Again, if I increase the k value beyond certain value, roots go to the right hand side. So within these values of k, the roots are on the left hand side. Here it is stable. It is conditionally stable. For other values of k, the system is unstable. Okay, such a system we call it as conditionally stable, absolutely stable. Relative stability, I told you, is the quality of measure of how fast the transients die out in a system. This we have understood already. Right? So basically, you want to have a stable system. You have to see that the roots lie on the left hand side of the S plane. If the roots by chance come on the right hand side, the system will become unstable. So in dynamic systems, it happens. Some of the parameters, they keep changing. So for example, let us say, what I mean by parameters keep changing, you can understand that. Suppose I have a car like this. Correct? Now the thing is, this car is taking a high speed turn, let us say. So when the car is on the curve here like this, the centrifugal force is acting like this. There will be grip force here. They will be opposing this motion, lateral grip forces. The centrifugal force will be trying to pull the car this way, but these lateral forces will be keep trying to push the tire like this, so that the car can be on the path. But what is important over here is road friction, the friction between the tire and the road. By chance that value is alright, fine. If all of a sudden that value decreases, probably you will not have sufficient grip forces and the centrifugal force may simply pull out like this. So that's how the system while operation, they become unstable. Correct? So this is what exactly, like, suppose if you take aircraft, you are flying an aircraft. Okay. So sometimes what is going to happen, the turbulence which is here, which is acting on the system, may make the system unstable. So it will start rolling about this axis. So these possibilities are there, right? So that is what we are talking about. So mathematically, when we model, we can understand how exactly these kind of disturbances will create problem on the system. So for the time being now, you understand the definition of stability. So I hope you have got what you mean by stable, unstable, limitedly or marginally stable, absolutely stable, and conditionally stable system. Correct? So see, I told you very clearly, if the roots lie on the left hand side of the S plane, like what I have done here, the system will be stable. Right. If the roots lie on the right hand side of S plane, then the system will become unstable. If the roots are on imaginary axis or roots are lying at the origin, you will get a constant output, but depending on the user, you can decide whether it's limitedly or marginally stable, and that can be converted as a limitedly or marginally stable system. This can be again interpreted as stable or unstable depending on the user's requirement. Right. Now suppose you have a higher order system. How do we find its stability? Means suppose you have an nth order characteristic equation, whether the system is stable or not. So the best way is take this nth order characteristic equation, find all its roots, find roots. And if you find that the roots are all on left hand side, then you can declare the system as stable system. By chance, if the roots are on the right hand side, you can declare the system as unstable. But as the order increases, the number of roots also increase, and it becomes quite difficult to solve this equation and locate the roots. Probably nowadays we have MATLAB, we can do so. But what is the quickest, easiest way of doing this? So there is Routh's stability criterion available to check quickly whether such a system is stable or unstable. It will only tell whether the roots are on left hand side or on right hand side. It will also tell how many roots are on left hand side or right hand side. But it will never tell you what are the values of those roots. Okay. So now, suppose a characteristic equation is given like this. Then what you do is just draw a vertical line like this. Then you write s to the power of n, s to the power of n minus 1, s to the power of n minus 2, so on, s cube, s square, s1, s0, order, right? Then in the first row, you mark A0, then A2, A4, alternative terms, A6, A8, like this. Then in the second row, A1, A3, A5, like this. A7, you mark this way. Now you have to find out the elements B1, B2, B3, like this. B1 is given by A1, A2, minus A0, A3 divided by A1. Similarly, B2, if you want to find out, A1, A4 minus A0, A5 by A1. B3, you want to find A1, A6 divided by A0, A7 minus A0, A7 divided by A1. Like that, you complete this row elements. Next, you want to C1, C2, C3. To find C1, B1, A3 minus A1, B2 divided by B1. Okay, C2 is equal to B1, A5 minus A1, B3 by B1. So like that, all these row elements you complete. Okay, like this. This you call it as a Routh array. This you call it as Routh array. Routh array. After that, you check only the first column elements. Suppose all these elements are positive, provided A0 is positive. then the system is stable. All the roots are on left hand side. By chance, let us say C1 is negative and all other things are positive. It is unstable. Correct? Provided A0 is positive, right? And how many roots are on right hand side of S plane? This is positive. Let us say D1 is also positive. Positive to negative, one sign change. Negative to positive, another sign change. There are two sign changes. There are two roots are on the right hand side of S plane. Two roots are on right hand side of S plane. Okay. So now we will state like this. For a system to be stable, it is necessary and sufficient that all the elements of the first column of the Routh array must be positive if A0 is positive. If this condition is not met, the system is unstable. The number of sign changes in the first column of the Routh array is equal to the number of roots that are on the right hand side of S plane. Okay, that is the statement. Okay. Now if you have understood this, let us look at some simple examples. Let us check whether this system is stable or not. S to the power of 4 plus 8s cube plus 18s square plus 16s plus 5 is equal to 0. So coefficient of this is 1, next 18, next 5. Okay, next row 8, 16, here nothing is there, put 0. Then we have to find this element. 8 into 18 minus 1 into 16 divided by 8. You'll get 16. 8 into 5 minus 1 into 0 divided by 8. That is 5 itself. Again 16 into 16, 256. Minus 8 into 5, 40. Divided by 16. You'll get 13.5. Next, this is 0, this is 0. Next, 13.5 into 5 minus 0 divided by 13.5. 5 you will get. So, this is positive, all are positive, so system is stable. Now, let us take another example. 3s4, 10s cube plus 5s square plus 5s plus 2 is equal to 0. So, here again 3, 5, 2. Then here 10, then 5. There is nothing is 0, 0. 50 minus 15, 35 divided by 10 is 3.5. 20, 0 divided by 10 is 2. 3.5 into 5, 17.5 minus 20 divided by 3.5. So it is minus 2.5 by 3.5. Next is 0. So again this multiplied by this minus 0 divided by this, you will get 2. There is one negative. So it is unstable. And there is positive to negative, one sign change, negative to positive, another sign change. Two sign changes are there. So two roots are on right hand side of S plane. Okay, right. So okay, now here other example you take 1, 2, 3. 1, 2, 5. This is 1 into 2, 2 minus 2, 0 by 1 is 0. 3 minus 5 is 2 divided by 1 minus 2. Now when I divide something by 0 becomes infinity. So array breaks. Now how do we continue with that array? Now you replace S by 1 by Z. Correct? Then this becomes 1 by Z to the power of 5, 1 by Z to the power of 4, 2 by Z cube, 2 by Z square, 3 by Z plus 5. Reorganize. You will get another equation array. And from that again you rearrange the elements the same way. Okay. Now you have got one negative. System is unstable. There are two sign changes. Two roots are on the right hand side of S plane. Okay, whenever you encounter a pivot 0, then you can do this. Okay, let us continue some more examples in the next video. Till then, thank you.